Hello everyone. Today we're going to start comparing and contrasting different techniques to do circuit analysis. So up to now we only used the one technique that I showed you. We called it the universal circuit analysis technique, and that's my preferred way of doing everything, mainly because you can pretty much implement it to any circuit that you want without no exception. Same exact methodology, and it just takes the complexity of choosing a technique out of the problem, and I like that aspect, especially for the students who are starting to look at electrical engineering and circuit analysis. But I'm going to show you the other techniques, namely nodal analysis and mesh analysis, and we're going to do it to the same circuit side by side and kind of see that the point I'm trying to put across is that at the end of the day, all these three techniques are exactly doing the same thing using exactly the same basic physics. And therefore, it's really your choice which one you're going to pick, which one you're more comfortable implementing. And if you don't want to choose, you can always just stick to one way of doing it, and that should work for any circuit if you're doing it carefully. Okay, so this is the circuit that we're going to analyze. I'm going to start, obviously, using our beloved technique, the universal technique. So we first label the circuit. We're going to identify all the nodes and label them with voltage variables, and then define currents that are passing through the component. So this would be one node, and this would be another node, and it would be another node, and that concludes the nodes in the circuit. So now I'm going to start calling them variables. This I'm going to pick that as our ground. That we know I can call it 50 volts because that's the voltage, the equation for that component. You can call it V1 and then later on come back and realize that V1 is 50 volts when you write the equation for that component for the source. And I'm going to call this one V1. Then I'm going to start labeling currents. So this would be I1, and then the current passing through the 5 ohm would be the same because I can write KCL right there and immediately realize that that's I1. I can call it a different current and then come back and write KCL. Obviously, this is a shortcut in our technique. I'm going to call this I2, call this one I3, and this one obviously I can call it I4 and then come back and write the equation for this component, which would be the current is equal to 3 amp. So I'm just going to call it 3 amp then. I don't have to call it something else. And at that point, I'm done labeling the circuit. So we move on to writing KCL, an equation for components. So we have 3 nodes. We have 3 KCLs to write, but we normally don't need to write it for the node, for the reference node. So we can write KCL for that node and that node. That one we already wrote the KCL at the time that we were labeling it. So the only KCL left is this one. So KCL for that node would be the currents going in are I1 and 3 amps. So I1 plus 3 is equal to the currents that are leaving the node, which is I2 and I3, and that's our KCL, the only KCL that we need to write. Then the equations for components, and now we have 1, 2, 3, 4, 5 components. 2 of these components, the sources in the circuit, we have already used the equation for those 2 sources to label that voltage and label this current, so we don't have to do those, and there are 3 equations left. So equation for 5 ohm resistor is I1 is equal to 50 volts minus V1 divided by 5 ohm, which is basically the Ohm law for that resistor. This one is I2 is equal to V1 minus 0 divided by 10 ohm. And finally, I3 is equal to V1 minus 0 divided by 40. Now, when it comes to solving this, one of the simplest way of doing it is obviously to use a calculator. Other than that, you can use the technique, the general matrix-based technique that I taught you. If you're doing it with hand, simply take the current equations, put them into KCL. That gets rid of all the current and unknown currents, and then in this case it just gives you one equation with one unknown V1. So that would be 50 minus V1 divided by 5 plus 3 is equal to V1 divided by 10 plus V1 divided by 40. Now with that I can multiply both sides by 40, and that would be 8 times 50, 400 minus 8 V1 plus 40 times 3 is 120, 4 V1 plus V1. So 5 V1 and then 8, that would be 13 V1, and added to those two to each other, that would be 520. So 13, I still have, so from this I can actually calculate V1. I'm going to look up the answer quickly here, make sure. So V1 ends up being 40 volts if I'm not mistaken. So let's just check that. 40 times 13, that actually gives you 520, which is the result of that. So once you have V1, you can actually put it back in this. It gives you I1, which ends up being 50 minus 40 divided by, which is 10 divided by 5. That's 2. From this one, 40, that's 4. And then finally, 40 divided by 40, 1 amp. So now you know everything there is about that circuit, and done. So this is how we do it using our technique, the universal technique that we normally use. Now let's start doing it in the other two ways. That one of them is called the nodal analysis. The other one is called the mesh analysis. So this is the nodal, and next we're going to do mesh. Okay, so what do we do in nodal analysis? Nodal analysis is actually quite similar to the technique that we use. We're going to still start by identifying nodes. So identify the nodes. That's similar to what we did before. So these are the nodes. Pick a reference. Do the same here. And that would be our 50 volts again, and this would be V1. Good. And then we're not going to actually label the currents for this specific technique. Instead, we're going to go to these nodes and start writing any node that is unknown. So this one has a known value, 0 volts. That one has a known value of voltage, is 50 volts, and V1 is the only one with an unknown. Now, why are we doing that? Really, the technique is optimized to relatively quickly give you values for voltages or electrical potential of nodes in the circuit. And therefore, since you already know the potential for these two nodes, you don't need to write any equation for them. So you start writing them for any node with an unknown potential, which would be in this case V1. And what you do is that you write KCL for that node, assuming that the currents are all leaving that node. In other words, without really calling them or putting a parameter here, you assume that there's a current leaving V1 in this direction, and there's a current leaving V1 in that direction, there's a current leaving V1 in that direction, and then there's a current leaving V1 in that direction. And then what you do is that you say, since they're all currents are leaving that node, you add them up, they have to be equal to 0, right? All the currents that are leaving the node, when you add them up, they have to be equal to 0. KCL, basically. All the currents coming in is equal to the currents leaving. Since all the currents are leaving, so currents coming in are 0, so you add up the currents that are leaving and it's equal to 0. And you start writing the equation for the currents that are leaving that node. In other words, if there was a current leaving that node, the equation that defines that current is this voltage minus that voltage divided by resistance. Ohm law for the 5 ohm. So that means that V1 minus 50 divided by 5 is leaving that node. So next current, the current that is passing through at 10 ohm, again, there's a current leaving that node, and the equation for it would be V1 minus 0 divided by 10. For the 40, same thing, V1 divided by 40. And then finally, if there's a current leaving this node and there's a current source which injects current into it, therefore the current that is leaving that node is equal to, if you assume it's leaving that node. Obviously there's a current that is getting injected to the node, but if your assumption or convention you're using is that there is a current leaving that node, then that current has to be negative of the 3 amp. And done. So this quickly gives you an equation that is going to now basically, after solving it, you're going to get the value for V1 using just one equation. And if you notice, actually this equation, once you manipulate it, it's exactly the same as that equation. So just moving the components around, if I move this to the other side and this 3 to the other side, then this equation is exactly the same as that equation. And so therefore, once I solve it, I get V1 that is equal to 40 volts. And at this point, since I have all the voltages for the nodes, I can then start calculating the currents using any equation that I know for the components, for example, the Ohm laws, if I need the values for the currents that are in the circuit. Now, and this basically concludes the calculation unless you need anything else. Now, if you need anything else, then you have to continue. For example, if you now need to know what current is passing through 5 ohm, you put the 40 back in this equation and you say, okay, 40 minus 50 divided by 5, that would be minus 2, at which point that indicates that this current is actually going the other way around. And then you do the same for this one, that one, and then you have calculated all the currents. So I'm going to leave it at this and then go back and kind of compare and contrast later so that we have a better idea what is going on. Now, for the last method, it's called the mesh analysis. This time we define loops. Loops of current are components that you can actually pass through them one after the other, start from a starting point, and then once you pass through a certain number of components, you go back to the same point that you started. That's a loop. So I can define a loop as like this, for example, here. I can define a loop, another loop that is like this here. And the direction of the loop is arbitrary. And I can define another loop that goes like this here. Now, this time, as opposed to what we saw before, we're not going to identify any nodes. Instead, we only focus on these few meshes that we defined, 3 mesh specific to be specific, and then define currents for these mesh or loops that we define. So I'm going to call this one I1, and call this one I2, and finally call this one I3. Now, notice that this current I3 is actually passing through this component, which imposes 3 amp to pass through the component. Therefore, I3, this current has to be equal to 3 amp. So that one, the current for that specific node is known, therefore. So this is equal to 3 amp. Good. So then I'm going to start doing something that is called KVL. And we haven't discussed KVL, but it's a very intuitive concept. What it says is that if you start in a loop, you start from any point in the loop, and you go through all the components and go back to the same spot, and you add up the voltages across all the components. Once you go back to the same point, the equation on when you add all the voltages, the equation has to be equal to 0, which is kind of obvious in a sense that what's the voltage? It shows the differences in potential or energy, potential energy of the system. So what it says is that if you go through a loop, every time that you gain a potential, you add something or subtract something, and then if you lose potential, you do exactly the opposite. So as you add or subtract potential, every time that you pass through a component, once you go back to the same potential, obviously the difference between the potential that you have has to be 0 because you're in the same spot. It's like you go in terms of gravity, you go up and a little bit down, again up and then down, and then if at the end of the day you go back exactly to the same level, then your potential difference is still the same because you're back to the same reference point. So it's kind of a dual of KCL, but KCL was with electrons going in and out of a node. The KVL is the dual of that with energy or potential when you go through a loop, and it's kind of intuitive. It says basically with electrons, we were saying that electrons don't generate out of nothing or don't dissipate, and with the potential, we say the energy doesn't generate out of nothing or come or disappear to nothing. So it's really the dual of what we had in KCL. Any potential that you gain and lose when you go back to the same level of potential has to come down to be 0 because you're at the same potential level. So we're going to exactly do that in the loop and start using a convention for that to write these equations. So what we write here is that I'm going to start from any point, so I can start, say, and go through the loop in the same direction that current is passing. So every time that I lose a potential, I'm going to put a negative sign, and every time that I gain a potential, I'm going to put a positive sign, or the other way around, depending on what my convention is. So let's assume that I'm going to say that every time that I lose a potential, I put a negative sign, and every time that I gain a potential, I put a positive sign. So going through the 5 ohm, the potential difference that I lose across the resistance based on Ohm law would be 5 ohm times the current I1. So minus, let's say I start from that node, minus 5 I1. Then I get to the 10 ohm. Now, notice that for the 10 ohm, there are actually 2 currents that are passing through the 10 ohm. There's an I1 that is going down, and there's an I2 that is coming up. So there are 2 currents in 2 directions, and I have to take both of them into account. And since I don't know which one is larger, which one is smaller, I just use a convention. I start with the one in the loop that I'm going through as being the first current, and then use the other one as the second that I subtract from the first one. So therefore that becomes minus 10 times I1 minus I2. So this is the current that is passing through 10 because the current is I1 going down and I2 going up. So I take the difference, then multiply by the 10 ohm, and then I'm losing that. And then finally I get to this, and going through this, I'm actually again going to subtract 50 ohm from, take, this time I'm gaining potential, so that would be a positive, and that would be equal to 0. Going back to that. So that's one equation. I go to the next one, and I write, starting, let's say I start from the same node. So again, here I have current I2 going through the 40 ohm and current I3 which is 3 amp going through 40 ohm, and they're both in the same direction, so they add up, and then I'm losing potential there, so that would be 40 ohm, sorry, 40 ohm times losing potential, I2 plus 3, then going back up. This time I2 is the current, my current, so that would be minus 10 times I2 minus I1 is equal to 0. And for this loop, I don't need to write an equation because the current of that loop is actually known as 3 amp. The same as where here I didn't have to write a equation for that node because the voltage of that node was known. Here the current of this loop is known, so I don't have to write an equation for it. With that, now I have 2 equations and 2 unknowns, and I can solve that. So let's see. From the first one, I have minus 15 I1 plus 10 I2 plus 50 is equal to 0. So from this, I can actually calculate I2 and put it in the second equation. So I2 would be equal to 50, be equal to 15 I1 minus 50 divided by 10, which would 1.5 I1 minus 5. So I can take that, put it in here. So minus 40 I2 minus 120 that's actually, so minus 40 I2 minus 10, it would be minus 50 I2 plus 10 I1 minus 120 is 0. I put that equation here, so that becomes minus 50 times 1.5 I1 minus 5 plus 10 I1 is minus 120 is 0. So 50 times 1.5, that would be 75, so minus 75, and then plus 10, that would be minus 65, so minus 65 I1, that is 250 minus 120, so that's equal to 250, that would be 130, so onto the other side, minus 130, so from this I1 is actually equal to 2 amp. So that's 2 amp. Then I use 2 in this equation, and that gives me I2, which ends up being equal to minus 2 amp. Okay, so this concludes the calculation here. Now let's go back and start comparing and contrasting. Okay, so what we did here was relatively long compared to both of these techniques. Why am I saying that? Because we have 4 equations for this one, only 1 for this one, and 2 for this one. So it appears that this one is actually the lengthier of all. But the one thing that I want you to notice is that once you're done solving this set of equations, you actually have calculated all the currents for each one of the components and all the voltages which for each one of the nodes. Whereas, for example, for this one, you have only calculated 1. Obviously, you have reduced the number of equations, but that one equation only gives you 1 unknown. You can then keep on going to calculate the rest of the unknowns, so you have to take that into account. So it's not much smaller. Now, what's the advantage? If, for whatever reason, the voltage of that node was the only thing that you were looking for, then you didn't have to solve a large set of equations. You only focus on this one equation and calculate that voltage and move on. So that's the advantage. Here you have two equations, therefore you're going to get two unknowns and the values for those two unknowns. But again, if you're looking for other things in the circuit, like the voltages across the components or anything like that, this hasn't solved any of that for you yet. You have to take these currents that you have calculated and then go back and calculate the voltages. And with this, since you haven't picked as reference, the voltages that you calculate are going to be the voltages across components as opposed to potential of each node. What's the advantage? Well, if you were looking for a current, specific current, this would give you that current faster because you don't have to solve 4 equations, you're only solving 2 equations. For example, if you wanted to know what that current is, then these two would directly give you I1, which is 2 amp. Now, look at this. I1 in this loop is the current through the 50 volt and also current through the 5 ohm, which would be I1 for that, and we calculated I1 to be 2 amps. So for both cases, obviously we get the same result. One thing that I want you to notice is that these currents are not the currents passing through each component. These currents are kind of an abstract concept that are currents through the loop. Sometimes the current through the loop is the same as the current passing through a component. For example, when the loop is not sharing any component with any other loop, the current of the loop is the same as the current of the component. But for the 10 ohm, where the 10 ohm is actually shared by the 2 loops, the current through the 10 ohm is not I1 nor I2. So once you calculate I1 and I2, then you have to go back and calculate the current passing through the 10 ohm. So with this, you just see that the current going down is 2 amp, the current going up is minus 2 amp, so the current that is passing through is the 2 minus the minus 2, which is 4 amp. In other words, the I2 is also going the other way around, so the 2 add up and give you the 4 amp, which is the same current that we calculated before. Okay, so there's still, you have to do some more analysis in order to specifically calculate the equation, the value for the currents of each component. At the end of the day, this one was directly the same equation. Once you take the equation for components and put it KCL, you get exactly the same equation. So it's as if you start with this and then you simplify it so that the number of equations go down, and you then calculate, get rid of certain parameters and calculate the one unknown that you have, and then you can go back, which is basically saying, I'm going to write the whole thing and then put the equations for the current into that equation. Here, kind of the same thing, in a slightly different way. This is actually the same concept. This time you get rid of voltages, actually, and then you get only equations based on current. So you could have done that here by basically getting rid of the voltages and basically reducing the number of equations into 2 that only have currents as unknowns, and you would get the same result. Between all 3, this one is my preferred method. Next lecture, I'm going to show you where times in circuits where these 2 don't work exactly the same way that we explained. In other words, there are exceptions when you're using any of these methods, whereas this one is always standing. And because of that, you have to start learning some techniques to kind of cover the exceptions for these 2. There is no exception for that one, and you can always implement it exactly the same as before. I'm going to stop at this point and do some more discussion about the differences and similarities of these techniques, or advantages and disadvantages, next time. Thank you.